Dear learners, welcome to the third module of chapter Alcohols, Phenols and Ethers. In the previous modules, we have discussed about naming, structure, preparation and properties of alcohols. Today, we will study about phenols. After today's discussion, you will be able to classify phenols, familiarize with the common names of phenols, name phenols according to the IUPAC system of nomenclature, relate the reactions involved in the preparation of phenols, analyze the chemical properties of phenols, analyze and interpret data to explain trends in the physical properties of phenols. You will also be able to plan and conduct experiments to identify a phenol in the lab. Till now, you have learned that substitution of one or more hydrogen atoms from a hydrocarbon by another atom or a group of atoms result in the formation of an entirely new compound having altogether different properties and applications. Phenols are formed when a hydrogen atom in an aromatic hydrocarbon is replaced by OH group. Phenols are widely used in household products and as intermediates for industrial synthesis. For example, phenol itself is used in low concentrations as a disinfectant in the household cleaners and in mouthwash. Phenol may have been the first surgical antiseptic. Today, we are going to discuss about the classification, nomenclature, preparation and properties of these organic compounds, that is, the phenols. In case of alcohols, phenols also may be classified as mono, di, tri or polyhydric compounds depending upon whether they contain 1, 2, 3 or many OH groups respectively in their structures, as you may see on the slide. The benzylic alcohol, in these alcohols, the OH group is attached to the sp3 hybridized carbon atom next to an aromatic ring. For example, you can see on the slide, on the benzene ring there is a carbon and the OH group is linked to that carbon. Compare these with allyl alcohols. Do you find any similarity? CH2 double bond CH, CH2OH, that was allyl alcohol. And now, when we compare this with a benzene ring with a carbon and then OH, isn't there a similarity? We also learnt about vinylic alcohols in the previous module. These alcohols contain OH group bonded to a carbon-carbon double bond, that is to a vinylic carbon. These are compounds containing OH groups linked to sp2 hybridized carbon. Similarly, you may compare a phenol with vinylic alcohol. Just remember, a phenol has benzene ring containing the OH group. That means a sp2 hybridized carbon is carrying the OH group. The OH group linked to an aryl carbon is shown in the slide. I am sure now you can differentiate between allylic, benzylic, vinylic and phenols. Understanding this classification is very important as these structural changes affect the properties of the compounds with OH groups. Let us now study the nomenclature of phenols. The simplest hydroxy derivative of benzene is phenol. It is its common name and also an accepted IUPAC name. As structure of phenol involves a benzene ring in its substituted compounds, the term ortho for 1,2 disubstituted, meta for 1,3 disubstituted and para for 1,4 disubstituted are often used in the common names. Let's have a look at the slide. So, you can see the structures and how ortho, meta and para compounds are written. To understand the physical and the chemical properties of organic compounds, it is very important to understand their structures. If we analyze and understand the structures, there will be no need to memorize the chemical reactions and properties. Let us observe the structural aspects of phenols in the slide. Compare this with water, where the HOH bond angle is 104.5 degrees and the bond length is 96 picometers or 0.96 angstroms. And for methanol, the ROH bond angle, as you studied in the previous module, is 108.9, whereas it's 109 in phenols. In phenols, the OH group is attached to the sp2 hybridized carbon of an aromatic ring. The carbon-oxygen bond length, that is 136 picometer in phenol, is slightly less than that in the methanol. This is due to the partial double bond character on account of the conjugation of unshared electron pair of oxygen with aromatic ring and the sp2 hybridized state of carbon to which the oxygen is attached. Have a look at the slide. So, now after understanding about the structure of phenols, let's have a look how phenols are prepared. So, phenols are also known as carbolic acids because they were first isolated in the early 19th century from coal tar. Nowadays, phenol is commercially produced synthetically. In the laboratory, phenols are prepared from benzene derivatives by any of the following methods. So, first of all, let's see the preparation of phenols from haloarenes. We have studied this in the chapter alkyl and aryl halides too. Chlorobenzene is fused with NaOH at 623 kelvins and 320 atmospheric pressure. Phenol is obtained by acidification of sodium phenoxide so produced. It may also be produced from benzene sulfonic acids. Benzene is sulfonated with oleum and benzene sulfonic acid so produced form is converted to sodium phenoxide on heating with molten sodium hydroxide. Acidification of the sodium salt gives phenol. The third method is from disonium salts. A disonium salt is formed by treating an aromatic primary amine with nitrous acid. Nitrous acid is NaNO2 plus HCl at 273 to 278 Kelvin. That means you have to keep it cool. Disonium salts are hydrolyzed to phenols by warming with water or by treating with dilute acids. And the fourth method is from cumene. Phenol is manufactured from the hydrocarbon cumene. Cumene, that is isopropyl benzene, is oxidized in the presence of air to cumene hydroperoxide. It is converted to phenol and acetone by treating it with dilute acid. Acetone, a byproduct of this reaction, is also obtained in large quantities by this method. Now let's come to the physical properties of phenols, and the first physical property is boiling points. So, because of the hydrogen bonds, the boiling points of phenols are high, but not as high as alcohols. The second one is solubility. Solubility of alcohols and phenols in water is due to their ability to form hydrogen bonds with water molecules, as shown in the slide. The solubility decreases with increase in the size of the alkyl or aryl, that is the hydrophobic group. Several of the lower molecular mass alcohols are miscible with water in all proportions, but not phenol. After this, let's come to the chemical reactions. In this, the first type of chemical reactions are similar to what we studied for alcohols, that is, the reactions involving cleavage of oxygen-hydrogen bonds, that is, the acidic character. The acidity of phenols is evident by the reaction with active metals like sodium, potassium, aluminium, etc., as we saw for alcohols also. And in fact, phenols are better Bronsted acids than alcohols. That is, they can donate a proton to a stronger base, The reaction of phenol with metals, example sodium, aluminium and sodium hydroxide, indicate its acidic nature. The hydroxyl group in phenol is directly attached to the sp2 hybridized carbon of benzene ring, which acts as an electron withdrawing group. Due to this, the charge distribution in phenol molecule as depicted in its resonating structures takes place. This causes the oxygen of the OH group on the phenol to be positive. The reaction of phenol with aqueous sodium hydroxide indicates that phenols are stronger acids than alcohol and even water. Let us examine how a compound in which hydroxyl group attached to an aromatic ring is more acidic than the one in which hydroxyl group is attached to an alkyl group. The ionization of an alcohol and a phenol takes place, as you can see on the slide. Due to the higher electronegativity of sp2 hybridized carbon of phenol to which the OH group is attached, the electron density decreases on oxygen. This increases the polarity of OH bond and results in an increase in the ionization of phenols as compared to that of alcohols. Now, let us examine the stabilities of alkoxide and phenoxide ions. In alkoxide ion, the negative charge is localized on oxygen, while in phenoxide ion, the charge is delocalized. The delocalization of negative charge gives you 5 structures. This makes phenoxide ion more stable and favors the ionization of phenols. Although there is also a charge delocalization in phenols, its resonance structures have a charge separation, due to which the phenol molecule is less stable than phenoxide ion. You can also see that a phenol molecule gives you only 2 resonating structures. Now, let us have a look at orthonitrophenol, metanitrophenol and paranitrophenol. Orthonitrophenol has a pK value of 7.2, that of metanitrophenol it is 8.3, whereas for paranitrophenol it is 7.1, and phenol has a pK value of 10. Orthocresol has 10.2, metacresol has 10.1, paracresol has 10.2 again, and ethanol is 15.9. We talked about these in the previous module also, but here you can see because nitro groups are electron withdrawing, they increase the acidic character of phenols, whereas the methyl group being electron donating decrease the acidic character of phenols. So, before we move ahead, let us see how to identify phenols in the laboratory. All phenols react with ferric chloride to form a coordination compound and give characteristic colors. So, let us see, let us perform this experiment, reaction of ferric chloride with phenol, and we will also see how phenols react with blue litmus. So, here let us perform an activity to see how to test for presence of phenols in the chemical laboratory. We have already said that phenols give characteristic colors with ferric chloride, and I will say it again that whenever you are using chemicals, use a bare minimum quantity, because the chemicals thrown down the drain come back to you in your food chain. So, here I have taken a very little quantity of phenol, and to this I am adding a small amount of ferric chloride. You can see the color change, it looks a little black, does it? Okay. So, let me dilute it so that you can see the correct color change, and for this I will keep a white filter paper. Let us see the color change. Are you able to see? Is it looking violet? So I am sure you can see the beautiful violet coloration that has appeared by adding ferric chloride FeCl3 to phenol. So dear learners, here we saw an activity to find the presence of phenolic group in the lab using ferric chloride. Now we wish to check the acidic character of phenols. We had checked for alcohols that alcohols do not turn blue litmus to red. Let us check it out for phenols. So again, a small quantity of phenol, and to this I will add the blue litmus solution. Okay? And we know that acids turn blue litmus to red. So phenol and few drops of blue litmus. So can you see the color change from blue to red? Because phenol has turned the blue litmus to red, that means they are fairly acidic in nature. Great. So I am sure you have understood these two properties of phenols with the experimentation. You should not hesitate to do experiments wherever and whenever possible. So dear learners, we are studying about the chemical properties of phenols due to cleavage of OH bonds. The first one we studied about the acidic nature. The second one coming up is esterification. Alcohols and phenols react with carboxylic acids, acid chlorides and acid anhydrides to form esters. In substituted phenols, the presence of electron withdrawing groups such as nitro group enhances the acidic strength of phenol. This effect is more pronounced when such a group is present at ortho or para position. It is due to the effective delocalization of negative charge in the phenoxide ion that this happens. On the other hand, electron releasing groups such as alkyl groups in general do not favor the formation of phenoxide ion. So, you can see the result of formation of an ester with phenols. Now, let us come to the reactions involving cleavage of carbon-oxygen bond, but this takes place only in alcohols. The reaction with phenol involving cleavage of CO bond takes place only when it is reacted with zinc, and no other reaction, as we saw in case of alcohols, takes place with phenols. So now let us come to some specific reactions which are given by phenols. These are electrophilic aromatic substitution in phenols. The reaction that takes place on the aromatic ring are electrophilic substitution reactions. The OH group attached to the benzene ring activates it towards electrophilic substitution. Also, it directs the incoming group to ortho or para position in the ring. These positions become electron rich due to the resonance effect caused by OH group. The resonance structures were shown under acidity of phenols. Common electrophilic aromatic substitution reaction takes place in phenols as follows. So, let us see the first electrophilic substitution on phenol, and that is nitration. With dilute nitric acid, even at low temperatures, phenols yield a mixture of ortho and para nitrophenols. We get a mixture. The ortho and para isomers can be separated by steam distillation. For this, we use the physical property of boiling points. The orthonitrophenol is steam volatile due to the intramolecular hydrogen bonding, while paranitrophenol is less volatile due to the intermolecular hydrogen bonds, because there are so many para-nitrophenol molecules that get linked to each other. This causes association of the molecules. With concentrated nitric acid, phenol is converted to 2,4,6-trinitrophenol. The product is commonly known as picric acid. You can see that the name of the product containing OH group is given the name acid. That means it is really acidic in nature. The yield of the reaction product is poor. Nowadays, picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converts it to phenol 2,4-disulfonic acid, and then the concentrated nitric acid to get 2,4,6-trinitrophenol. Can you write the equation of the reaction involved? So, dear learners, the electrophilic substitution of nitro group. Let's do this with an activity, and after seeing me, you should perform it in your labs also. While performing experiments, you have to be careful with the chemicals, and so I am taking a little amount of phenol, as you can see, and to this I will be adding concentrated nitric acid. Concentrated nitric acid has to be handled carefully. So, that is why I have a red cap here, so that you have to handle carefully, and you can see the fumes arising. That is why concentrated nitric acid is also known as fuming nitric acid. Okay. So, a little amount of fuming nitric acid and you get the product. Okay. If I dilute this, you will get a yellow colored precipitate. Isn't that beautiful? The yellow colored precipitate can be separated, and that is what picric acid, 2,4,6-trinitrophenol. So, dear learners, can you see the PPT getting formed, and now yes, it is settling down also. The yellow colored PPT is of picric acid, that is 2,4,6-trinitrophenol. Let us see another chemical property of phenols, that is halogenation. It is also an electrophilic substitution reaction. On treating phenol with bromine, different reaction products are formed under different experimental conditions. When the reaction is carried out in solvents of low polarity, such as CHCl3 or carbon disulfide, and at low temperatures, the mono-bromophenols are formed. The usual halogenation of benzene takes place in the presence of a Lewis acid, you know that, such as FeBr3, which polarizes the halogen molecule. But in case of phenols, the polarization of bromine molecule takes place even in the absence of Lewis acid. It is due to the high activating effect of the OH group attached to the benzene ring. So, as you can see on the slide, the phenol gives orthobromo and the para-bromo products. Para-bromo product is major. But when phenols are treated with bromine water, a 2,4,6-tribromophenol is formed as a white precipitate. So, dear learners, this 2,4,6-tribromo derivative of phenol can be also prepared very easily in the lab. Let us do it here. So, here I have some phenol, a little amount. To this I will add bromine water, which I have prepared. So, by adding bromine water, and a little friction to warm it. So, yes, here we have got a white PPT of 2,4,6-tribromo-phenol. You can perform this experiment in the lab. The next reaction that phenols give is Kolb's reaction. The phenoxide ion generated by treating phenol with sodium hydroxide is even more reactive than phenol towards electrophilic aromatic substitution. Hence, it undergoes electrophilic substitution with carbon dioxide, a weak electrophile. Orthohydroxybenzoic acid is formed as the main reaction product. Let's see another reaction of phenols. Riemer-Tiemann reaction, a very important name reaction. On treating phenols with chloroform in the presence of sodium hydroxide, a CHO group, that is an aldehyde group, is introduced at the ortho position of the benzene ring. This reaction is known as Riemer-Tiemann reaction. The intermediate substituted benzyl chloride is hydrolyzed in the presence of alkali to produce salicylaldehyde. You remember salicylic acid? Okay. The next reaction is reaction of phenol with zinc dust. Phenol is converted to benzene on heating with zinc dust. That is, we also said that this is the only reaction in which the carbon-oxygen bond can be cleaved. So, when phenol is treated with zinc dust and heated, you get simple benzene. Let's see the next reaction for the phenols, oxidation. Oxidation of phenol with chromic acid produces a conjugated diketone known as benzoquinone. In the presence of air, phenols are slowly oxidized to dark colored mixture containing quinones. So, my dear learners, to summarize today's discussion, we began with understanding the structure, classification followed by naming of phenols. We also learned methods of preparation of phenols from haloarenes, benzene sulfonic acids, diazonium salts and cumene. We learnt about the physical properties of phenols as to their boiling points and solubility in water. Under chemical properties, we learnt about the acidic nature of phenols and also the electrophilic aromatic substitution. Under this, we had halogenation, nitration and sulfonation reactions. Besides this, we also studied some name reactions, namely Kolb's reaction and Riemer-Tiemann reaction. And lastly, the oxidation of phenols. So, dear learners, before we end today's discussion, let me leave you with an assignment. I am sure you can do it, and I hope you have understood the concepts discussed in today's discussion. I am also sure that you are looking forward to some interesting and amazing concepts related to phenols. But till then, take care.